everyone, I am Stephanie Graciton, a third year BS Ed major math student. Today, I'll be talking about normal subgroup and quotient group. In 1798, at the age of 21, Carl Friedrich Gauss wrote a classic book called The Disquationes Arithmetica. Here, he laid out the modern idea of modular arithmetic. This technique takes the group of integers, partitions them into a finite number of sets, and then treat each set as a new type of number. Modular arithmetic has proven to be so useful, it's natural to try to adapt this technique to other areas. In group theory, this can be done using normal subgroup and quotient groups. Normal subgroup is let H be a subgroup of J, and we may write that like less than or equal to symbol but without triangle. Instead of a less than, we may write H is a normal subgroup of J like that. If H is closed with respect to conjugates, the conjugate of an element A is any element of the form X as X inverse, where Xn and the X inverse can come from the containing group G. They don't have to come from the subgroup H. So for H to be closed with respect to conjugates means that any element A of H has all of its conjugates also contained in H. Again, if we take an element X from the containing group J, X and X inverse is a conjugate of the element A. It must be the case that all conjugates of all elements of H are also in H for H to be a normal subgroup. Let's unwind this definition for a moment. Let's unwind the definition for a moment just to see all the restrictions on a normal subgroup. A normal subgroup of a group J is going to be a non-empty subset of J that is closed with respect to three things: product, inverses, and conjugates. Being closed with respect to product and inverses is what makes it a subgroup. And then the additional restriction of being closed with respect to conjugates is what will make it a normal subgroup. And here an equivalent definition, which at a glance probably looks a little bit nicer. Some books will use this as a standard definition. H is called is normal subgroup of the group J if every left coset of H is equal to its respective right coset. So for subgroup H to be a normal subgroup, there must be no difference between its left and right coset. Keep in mind that saying each left coset AH is equal to its corresponding right coset HA is not saying that each AH is equal to HA. This is not true in general. It's just the whole cosets that are equal to the individual elements may not correspond in this particular way. First example, we'll consider this set and containing the identity permutation and these other two permutations. F is a normal subgroup of the symmetric group S3. Let's just take a second to look at the conjugate condition. If we just take for granted that N is a subgroup, for it to be a normal subgroup, it must be closed with respect to conjugates. So for example, if we take this element from N, the permutation 1, 2, 3, all of its conjugate must also be an N. Remember, a conjugate is any element of the form x 1, 2, 3, x inverse, where x can be any element of the group S3. This is the form of any conjugate of this particular element 1, 2, 3. So let's look at one example of a conjugate of this particular permutation. We're going to compose an element on the left and will compose with its inverse on the right. In this case, the permutation 2, 3 is its own inverse. So the conjugate looks like this, and take note that this permutation 2, 3 is an element of the group S3. So this is a valid conjugate. And if we go through this composition of permutations from right to left is equal to this permutation, which is the element of N as we expected. You can see how this composition of permutations map 2 to 3, but then maps 3 to 1. So in total, 2 gets mapped to 1, then it also 3 to 2, but then that gets mapped to 3. But then that gets mapped back to 2. So in total, 3 get mapped to 2, 1 is mapped to 2, and then in total is mapped to 3. So you can see that this composition of permutations equals this, which is an element of n. And if I check the rest of the conjugates for all elements of n, you will see that it is close with respect to conjugates. Thus, it is a normal subgroup. Thinking about the coset definition of a normal subgroup, we would also look at the left and right cosets of n using this element 2, 3. And those look like this, and as we would expect, they are indeed equal. Looking at the left coset first, 2, 3 composed with the identity is just 2, 3. 2, 3 composed with 1, 2, 3 is 1, 3. 2, 3 composed with 1, 3, 2 is 1, 2. And a similar string of calculations gives us the right coset, and you see that they are identical. And this would be the case for all left and right cosets of n. For n, since it is a normal subgroup, there is no difference between the left and the right coset. Again, thank you for listening and taking time to watch my video. I hope that you are enlightened about normal subgroup and quotient group. That's all. Thank you.